All right, guys, we're going to do our second inference with proportions review video. And so what we want to do is talk about the intervals that we discussed in video 1. We talked about getting those intervals, but we want to say, what can we do to change the size of those intervals? Okay, because they are estimating a value. Well, if we're estimating something and we're going from, you know, negative infinity to positive infinity, how informative is that? What can we do to change the size of that interval? So here's a picture of an interval. So this is your next page in your packet. So here's our interval with that point estimate in the middle. So in this case, if we had our p hat, that would be right there in the middle. And we want to see what can we do, to make this interval smaller or larger. Okay. Now, of course, as your p hat changes, then you're shifting those intervals up and down the number line. Okay, but changing the size of those margin of error is what's mostly affecting the size of the interval. So I have that right here. This p hat is that one in the middle, that point estimate is shifting back and forth and making that interval higher or lower. But what is changing the size of the interval is those margins of error. Okay, and so they're going to be making that wider or narrower based on these two items here that make up the margin of error. Okay, so we want to address those two things. How can we control them? Because you can't control your p hat. P hat is based on the results you got. Okay, so what we need to do is talk about what can you control. Well, since your critical value is a function of how confident you want to be, then that can change the size of our interval. So here is an example. We've got this situation. You can see that if you are 90% confident, then you have 90% of the data in the middle. And so therefore your critical values, negative and positive 1.645. Okay, but if you want to be 95% confident, then you have got a wider interval because you're encompassing more area in the middle. So then our critical values are larger. And so that's making that Z star a bigger number, and that's making our interval wider. Okay, so I think that's understandable. And then you can see, 99%, of course, would encompass even more data. Okay, so then that is making it wider. So in summary, if the higher you are more confident, then the bigger that critical value is, which is increasing the size of that interval. Okay, the other thing that has an effect that you can control, the other mechanism you can control is your sample size. Okay, so let's take a look back at that. So since our margin of error, if I just took that part and broke that part out of the formula, okay, I just said, okay, let me just focus on this. Margin of error equals Z star times that standard error. Okay, and so that's what I have here, and that's what I'm showing here. All right, so we know that if we kept the same critical value, we could change the size of the margin of error by changing the sample size. Okay, and we know, based on a lot of things that we've done in the past, as the sample size goes up, what is happening to that standard deviation? Okay, that standard deviation then is getting smaller. Okay, so that's something that we already are very familiar with. So here's an example. Let's kind of actually talk about specifically how much does the change in sample size affect the change in the margin of error. So here we go. Let's do this here. Make the sample size 4 times larger. Okay, so I have an equation here. If I make the sample size 4 times larger, 4n, Okay. And you know from balancing equations, you can't put something on one side without putting it on the other. So if I put in this 4 right here, then I have to balance it on the left-hand side by mimicking it with, or making it it's like 1 over the square root of 4, the square root of 1 over 4. So essentially what that is 1/2, because that square root of 4 is your 2. So in summary, what that says is, if we make the sample size 4 times larger, then what does that do to the margin of error? It makes it half as big. Okay? When we did our Hershey's Kisses lab, when you had your 100 sample size, but when we combined it with 3 other people, you now had a sample size of 400, and then that made the intervals smaller because we had smaller standard deviation. All right, let's take a look at what's happening here. What happens if you make the sample size 9 times larger? So I'm going to make this 9 times larger. Well, when that comes out to equate it on the other side, 1 over the square root of 9 is 1/3. So multiplying the sample size by 9 will shrink the interval to 1/3 of its previous size. Okay? And finally, what happens if it's 16 times larger? Because we usually they do it pretty simple in this first course. They do it in terms of perfect squares, so it's not all funky. But at any rate, no matter what it is, if you make your sample size that much bigger, it's making the margin of error by 1 over that square root. So in other words, in this case, 1/4. Okay, in general, you could say it is going to, as you get so much bigger, for every times you get bigger, your margin of error gets smaller by 1 over the square root of that change in n. Okay? All right. Now, the last item is this here, where we're interested in saying, okay, now that I know these mechanisms of change, okay, now that I know how to do this, how can I use that to my benefit? If I have a specific confidence level that I want to meet, but yet I do not want that interval to be too big, I want to define what the size of the margin of error is, okay, then what size sample should I take to meet that criteria? All right, so here we go. So scientists were wanting to determine the percent of Los Angeles marriages that end in divorce. So in the first year. So how large of a sample size do we need to do in order to make a estimate that is within plus or minus 0.07? That's your margin of error. Okay, that's saying how accurate they want you to be, and with 94% confidence. Okay, so that's going to be used to get your critical value. Okay, 0.94 isn't your critical value. You need to find the critical value. While you may use that confidence level, that's not it. That confidence level is what's in the middle. So in order to get that critical value, we know we're going to do inverse norm of 1/tail. Okay, and so if we had 94% in the middle, how much is that putting in each one of those tails? So that leaves 6% split. So each tail is 0.03. Okay, so I'm going to do inverse norm of my 0.03 to get that critical value. Okay, so in my calculator, I did that. I did second vars, inverse norm of my 0.03, and I got, I believe it's 1.88. Okay, so it gives me the negative. Okay, but remember we know from symmetry it's positive and the negative, so I just usually say the positive. So what I know so far is that my margin of error is 0.07, okay, and that my critical value is 1.88, okay. Now, This problem says, okay, let's go ahead and figure this out. Well, let's write our formula. Margin of error equals that critical value times that standard deviation. Okay, we should be able to fill in all of the data we need except for n. All right, so let's do that. I know that that margin of error is 0.07. We just computed this critical value is 1.88. Okay, then I got a square root, and I'm going to be solving for n. So p hat. What happens up here? Did we take a sample yet? We have not taken a sample yet. Okay, so we don't have a p hat. All right, so do you remember this song? The best it can be is if you use true p. Okay, but with our intervals, if you don't have that, you can just use p hat. And in this case, we don't even have a p hat. The worst case scenario is those don't jive. Please don't cry, just use 0.5. And when we learned this originally, we talked about why that is. That's the safest value because that makes the biggest product possible. So that's the reason, and I showed you that on the calculator at one point. But anyway, now, let's go through the calculator motions to solve this. And remember, this is one where there's so many decimal places that this can change very quickly, very fast. So we're going to go ahead and keep everything in our calculator. So let's solve this. What would I do first? And please don't tell me you're going to square both sides first. Okay? All right, the first thing I'm going to get rid of is this 1.88, so I'm going to divide both sides by that 1.88. Okay, so dividing both sides by that 1.88. So I've got my 0.07 divided by my 1.88. All right, and there it is. Okay, now after I have done that and I've got that 0.037 number, whatever that is, yada, 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 okay, then that's equaling this right here, this 0.5 times a 0.5 over n. Okay, so now what would be next? How do I get rid of this square root? I'm going to square both sides, so I'm going to square that. Over here on the left-hand side, I'm going to square that result, and see I'm keeping everything in the calculator so I can keep that accurate. There it is. Okay. Sometimes you get a number here that is actually crazy small, that's written in scientific notation that says something times 10 to the negative fourth or fifth or whatever. Okay, so hence this is why we kind of are using this keep it all in the calculator technique. And so then what I am left with is that product that I had, which was 0.001386, so on, so on, so on, 0.001386, and so on, dot, 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 whatever that is equaling this point, the 0.5 times 0.5, which I know is 0.25 over n. Okay, and so then remember, this is a very common mistake students make. You would multiply both sides by n. So the reality is, to get this to solve for n, you're going to take your 0.25 and be dividing it by this big old decimal here. Okay, so what that means is on my calculator, I'm going to put the 0.25 and I'm going to divide it by that god-awful number that it gave me in the previous line. So second answer, that's the second and the negative button, and therefore I get that. And I've got 180, so I need to have 180 and a third people. Can you have a third of a person? No. If I go lower than that, I am not going to be accurate enough. So 180, not accurate enough. 181 then is what I have to be accurate enough. Okay, so the minimum 181. A lot of times I see this in a multiple choice answer form where they're going to give you all the different answer choices and they'll say, which one of these is the smallest one to meet the criteria? And your answer choices would be something like 165, 175, 185, 195, and so on, and 205 or whatever. Well, the 175 and 165 don't meet the criteria. Okay, this is the best, this is the smallest number that will get me where I need to be. Okay, so in summary, we found that those mechanisms we can control are your confidence level, okay, and then your sample size, okay, and remember, let's do as your confidence level goes up. What does that do as you're getting a bigger confidence level? What happens to your interval? Your interval size goes down. Okay, let's say as n goes up, as you're increasing your sample size, what happens to the interval size? So the interval, what happens to the interval is then it would decrease standard deviation. So therefore, the interval would go down. Okay, I said this wrong a moment ago. Hold on. I said this wrong, didn't I? If your confidence is getting bigger, 90%, 95%, 99%, as confidence goes up, your interval is getting wider. There we go. I like that better, and I like that language better. And then as n is going up, it's making your standard deviation smaller, so it's less varied. Therefore, that would be then making your n going up would make it the interval get narrower. Okay, very good. That's how that is. Okay, that's the end of that video.